Now imagine you are floating in the absolute emptiness of space. There is nothing around you. No sound, no light, no warmth. Just the cold, infinite, silent vacuum of the cosmos, stretching in every direction for billions and billions of light years. You are alone in a way that no human being has ever truly been alone. And then, slowly, very slowly, a faint red glow begins to appear in the distance. It is so far away that at first you think your eyes are playing tricks on you, but it grows, it gets brighter. And as you drift closer, you begin to realize that this is not just a point of light. This is not just another star. This is something so unimaginably, so incomprehensibly enormous that your brain simply does not have the capacity to process what it is seeing. This single object, this single burning sphere of plasma and fire, is so large that if you placed it where our sun sits right now, it would swallow Mercury whole. It would consume Venus without even noticing. Earth, our entire planet, everything we have ever known, every city, every ocean, every mountain, every person who has ever lived, would vanish inside it like a grain of sand dropped into the Pacific Ocean. Mars would disappear. The asteroid belt would be gone. Jupiter, the largest planet in our solar system, a planet so massive that it could fit 1,300 Earths inside it. Jupiter itself would be swallowed, and this star would keep going. Past Jupiter, past the orbit of Saturn, its surface, its burning, churning, pulsating surface, would extend so far outward that Saturn and its magnificent rings would be hovering just near the edge, maybe just barely outside, maybe engulfed entirely depending on the day. Because this star breathes. It expands and contracts. It pulsates like a heartbeat, a slow, deep, cosmic heartbeat that takes months or even years for a single beat. And with each expansion it reaches further into the void. With each contraction it pulls back just a little, only to push outward again. This star is real. It exists right now, at this very moment, burning somewhere in the depths of the cosmos. And today, you and I are going to find it. We are going to understand it. We are going to trace its entire life story, from the moment it was born inside a cloud of gas and dust, all the way to the moment it will die in one of the most spectacular explosions the universe has ever seen. We are going to explore how scientists even figured out that something this big could exist. We are going to meet not just one colossal star, but an entire gallery of titans, each one larger than the last, each one pushing the boundaries of what we thought was physically possible. And along the way, we are going to ask questions that go far beyond astronomy. Questions about the nature of size itself. Questions about the limits the universe imposes on its own creations. Questions about what these dying giants mean for us, for our planet, for the very atoms in our bodies. Because here is something that might surprise you. The story of the biggest star in the universe is not just a story about a big ball of gas. It is a story about you. About me. About everything that exists. And by the end of this journey, you will never look at the night sky the same way again. But before we meet these cosmic monsters, before we climb the ladder of stellar size from the smallest stars to the most colossal, we need to start at the very beginning. We need to understand what a star actually is. And I promise you, even if you think you already know, there are layers to this story that are going to surprise you. Because the truth about stars, the real truth, is far more beautiful and far more terrifying than anything you learned in school. Let us begin with nothing. Literally nothing. Well, not exactly nothing. Let us begin with a cloud. Not a cloud like the ones you see in the sky on a summer afternoon. This is a cloud of gas and dust, floating in the vast emptiness between the stars. Astronomers call these clouds nebulae, from the Latin word for mist or cloud. And these nebulae are the birthplaces of stars. They are the cosmic nurseries where the universe creates its most magnificent objects. Picture the Orion Nebula, one of the most famous and beautiful objects in the night sky. It is a swirling, glowing mass of hydrogen gas, helium, and tiny grains of dust, stretching across dozens of light years. A single light year is about 9.5 trillion kilometers. So when I say this cloud stretches across dozens of light years, I am talking about a volume of space so vast that it dwarfs anything in our solar system by factors of millions. Inside this cloud, the temperature is incredibly low, often just 10 or 20 degrees above absolute zero, which is negative 273 degrees Celsius. At these temperatures, the gas molecules move sluggishly, barely vibrating, drifting through the cloud at a lazy pace. And the density is absurdly low. We are talking about maybe a few hundred or a few thousand molecules per cubic centimeter. For comparison, the air you are breathing right now contains about 25 billion molecules per cubic centimeter. These nebulae are emptier than the best vacuum we can create in any laboratory on Earth. And yet, despite being so sparse, so cold, so seemingly inert, these clouds contain the raw material for something extraordinary. Because hidden within this cloud is a force that is patient, a force that is relentless, a force that never ever gives up. That force is gravity. Gravity is the weakest of the four fundamental forces of nature. It is weaker than electromagnetism by a factor of about 10 to the 36th power. It is weaker than the strong nuclear force and the weak nuclear force by even larger factors. And yet, gravity has one advantage that none of the other forces possess. It is always attractive. It never pushes things apart. It only pulls things together. And it operates over infinite distances. It never turns off. It never gets tired. It just keeps pulling. And in a nebula, where trillions upon trillions of gas molecules are floating in close proximity, gravity is always at work, gently, imperceptibly pulling every molecule toward every other molecule. Most of the time, this pull is so weak that it is overwhelmed by the gas pressure and the random thermal motions of the molecules. The cloud just sits there, in a state of near equilibrium for millions of years. But sometimes something disturbs that equilibrium. Maybe a nearby star explodes as a supernova, and the shockwave from that explosion ripples through the cloud, compressing it. Maybe the cloud drifts through a spiral arm of the galaxy and encounters a density wave that squeezes it. Maybe two clouds collide, or a passing star's gravity tugs on a particularly dense region. Whatever the trigger, the result is the same. A region of the cloud becomes just a little bit denser than its surroundings. And once that happens, gravity takes over. The denser region has slightly more mass concentrated in a smaller volume. This means its gravitational pull is slightly stronger. It begins to pull in more gas from its surroundings. As more gas falls in, the mass increases, which makes the gravity stronger, which pulls in even more gas. This is what physicists call a positive feedback loop, or more dramatically, gravitational collapse. And once it starts, there is no stopping it. The region contracts. Gas falls inward from all directions, accelerating as it goes. As the gas compresses, it heats up, because when you compress a gas, you do work on it, and that work is converted to thermal energy. The temperature begins to climb. 10 degrees, 50 degrees, 100 degrees, 1,000 degrees. The collapsing cloud fragment, now much denser and hotter than its surroundings, begins to glow faintly in infrared light. It is not yet a star. Astronomers call it a protostar, meaning a precursor to a star in the making. And at this stage, it is powered entirely by gravitational energy. There is no nuclear fusion happening yet. The heat comes solely from the compression of gas under gravity. But the collapse does not happen in a simple, uniform way, because the original cloud was almost certainly rotating. Even if just slightly, the collapsing gas cannot fall straight to the center. Conservation of angular momentum, one of the most fundamental laws of physics, dictates that as the cloud contracts, it must spin faster. Think of an ice skater pulling in her arms during a spin. She speeds up dramatically. The same thing happens to the collapsing gas cloud. As it shrinks, it spins faster and faster. And this rotation causes the infalling gas to flatten into a disk, a rotating accretion disk, swirling around the central protostar like water circling a drain. This disk is where planets will eventually form, but that is a story for another time. For now, the important thing is what is happening at the center of this disk. The protostar is growing. Gas is streaming onto it from the disk and from the surrounding cloud. Its mass is increasing, its temperature is climbing, its core, the innermost region where the density and temperature are highest, is getting hotter and hotter and hotter. 10,000 degrees, 100,000 degrees, 1,000,000 degrees. And then, when the core temperature reaches approximately 10 million degrees Kelvin, something miraculous happens. Something that transforms a ball of collapsing gas into a star. Something that will power this object for millions, or billions, or even trillions of years. Nuclear fusion ignites. Let me explain what nuclear fusion actually is, because it is one of the most important and one of the most beautiful processes in the entire universe. At its core, fusion is about taking small atomic nuclei and smashing them together to form larger nuclei. Specifically, in the core of a newborn star, hydrogen nuclei, which are simply individual protons, are fused together to form helium nuclei, which contain 2 protons and 2 neutrons. Now, this sounds simple, but it is extraordinarily difficult to achieve. The reason is that protons are positively charged, and like charges repel each other. The electromagnetic force between 2 protons pushes them apart with enormous strength. To overcome this repulsion and bring 2 protons close enough for the strong nuclear force to take over and bind them together, you need incredible temperatures and pressures. You need the protons to be moving so fast, with so much kinetic energy, that they can overcome the electromagnetic barrier and get close enough to fuse. 10 million Kelvin is the threshold. At this temperature, the protons in the core of the protostar are whizzing around at hundreds of kilometers per second, colliding with each other billions of times per second. Most collisions result in the protons just bouncing off each other, but every once in a while, 2 protons get close enough, and quantum mechanical tunneling allows them to bridge the tiny remaining gap, and they fuse. The strong nuclear force grabs them and holds them together, and in the process, a tiny amount of mass is converted to energy, according to Einstein's most famous equation. E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is about 300 million meters per second. Squared, that is 9 times 10 to the 16th. So even a tiny amount of mass, when multiplied by this enormous number, produces a staggering amount of energy. And in the core of a star, this process is happening trillions upon trillions of times per second. The cumulative energy output is phenomenal. Our Sun, for example, converts about 4 million tons of mass into energy every single second. 4 million tons every second. And it has been doing this for 4.6 billion years. And it will continue doing it for another 5 billion years. That is the power of nuclear fusion. When fusion ignites in the core of the protostar, something fundamental changes. The energy released by fusion creates an outward pressure, a radiation pressure, that pushes against the inward pull of gravity. And for the first time, these 2 forces reach a balance. Gravity pulling in, radiation pressure pushing out. The protostar stops collapsing. It stabilizes. It becomes a star. This balance is called hydrostatic equilibrium, and it is the defining characteristic of every star in the universe. Every star, from the smallest red dwarf to the most colossal supergiant, is a battleground between these 2 opposing forces. Gravity wants to crush the star into oblivion. Fusion fights back with explosive energy. As long as this balance holds, the star lives. The moment one side wins, everything changes. And as we will see later in this video, when we talk about the deaths of the most colossal stars, the moment gravity finally wins is one of the most catastrophic events in the entire universe. Now, the star has been born. It has ignited fusion. It is in hydrostatic equilibrium. It enters what astronomers call the main sequence, which is not a place in space, but rather a phase of life. The main sequence is the longest, most stable period of a star's existence. It is the period during which the star is steadily fusing hydrogen into helium in its core. For our Sun, this phase lasts about 10 billion years. For smaller, cooler stars, it can last trillions of years, far longer than the current age of the universe. But for massive stars, the giants and supergiants that we are building toward in this video, the main sequence is shockingly brief. A star with 20 times the mass of the Sun will exhaust its core hydrogen in only about 10 million years. A star with 40 or 50 solar masses might burn through its fuel in just 3 or 4 million years. This seems paradoxical. These massive stars have far more fuel than smaller stars. They have more hydrogen. They should, logically, last longer. But they do not. Because the rate at which they burn that fuel is not proportional to their mass. It is proportional to something like their mass raised to the third or fourth power. A star 10 times the mass of the Sun does not burn fuel 10 times faster. It burns fuel roughly 10,000 times faster. It is like 2 cars on a highway. One is a small fuel-efficient hybrid with a modest tank. The other is a massive truck with a fuel tank 10 times larger, but the truck is driving at 10,000 times the speed. Despite having more fuel, it runs out vastly sooner. Massive stars live fast and die young. They burn with incredible ferocity, blazing with luminosities hundreds of thousands or even millions of times greater than our Sun. But their lives are measured in mere millions of years rather than billions. And when they finally exhaust their fuel, when the hydrogen in their cores is gone, the consequences are spectacular. But let me not jump ahead. Let me instead pause here and talk about something that is absolutely essential to understanding why the biggest stars look the way they do. And that is the difference between mass and size, because this is one of the most common misconceptions in all of astronomy. When I say the biggest star, most people assume I mean the most massive star, the star with the most stuff in it, the star that weighs the most. But that is not what I mean at all. In stellar astronomy, size refers to the physical dimensions of a star, its radius, how far its surface extends from its center, and mass refers to how much matter the star contains. These are 2 very different things, and here is the crucial insight. The most massive stars are not the largest stars by radius, not even close. The most massive stars we know of, objects like R136A1 in the Large Magellanic Cloud, which has something like 170 to 200 or more solar masses, are actually relatively compact. R136A1 is incredibly hot, incredibly dense, and blindingly luminous, but its radius is only about 30 to 40 solar radii. It is a blue hypergent, a compact scorching furnace of energy. Now compare that to a red supergent like Canis Majoris or WOH G64. These stars have masses of only about 20 to 40 solar masses, far less than R136A1, but their radii are over 1,000 solar radii. Over 1,000. They are physically hundreds of times larger than the most massive star we know, despite containing far less material. How is this possible? How can a star with less mass be so much bigger? The answer lies in stellar evolution, the process by which stars change over their lifetimes. When a massive star exhausts the hydrogen in its core, the core contracts. Without the outward pressure from hydrogen fusion, gravity squeezes the core down to higher densities and temperatures. This increased temperature ignites hydrogen fusion in a shell surrounding the core, a layer of fresh hydrogen that has not yet been burned. The energy from this shell burning is enormous. and it floods outward into the star's envelope, the outer layers of gas. This extra energy pushes the envelope outward. The star begins to expand. And as it expands, the outer layers cool down because the same amount of surface energy is now spread over a much, much larger area. The surface temperature drops from tens of thousands of Kelvin to just 3,000 or 4,000 Kelvin. And at these lower temperatures, the star glows red instead of blue or white. This is how a red supergiant is born. It is not a young, freshly formed star. It is an old star, a dying star, in the final stages of its life. The enormous size, the bloated, pulsating red atmosphere, that is the sign of death. The star is falling apart. Its outer layers are barely held on by gravity. In fact, many of these stars are actively losing their outer layers, shedding material into space at prodigious rates. They are, in a very real sense, slowly dissolving into the cosmos, and it is precisely in this state, this final, desperate, bloated state, that stars reach their maximum physical size. The red supergiants and hypergiants, the ones with radii of 1,000 solar radii or more, are all dying stars, every single one of them. They are magnificent, yes. They are awe-inspiring, but they are also tragic. They are the last gasp of a once mighty star, burning its final reserves of fuel before the inevitable collapse. There is a beautiful law of physics that governs this relationship between size, temperature, and luminosity. It is called the Stephenson-Boltzmann law, and it is one of the most elegant equations in all of astrophysics. The law states that the total luminosity of a star, meaning the total amount of energy it radiates per second, is equal to 4 times pi times the radius squared times sigma times the temperature raised to the 4th power. In symbols, L equals 4 pi r squared sigma t to the 4th. Sigma is the Stephenson-Boltzmann constant, a fixed number. Now look at what this equation tells us. Luminosity depends on 2 things: the surface area of the star, which goes as the radius squared, and the temperature, which goes as the 4th power. If you have 2 stars with the same luminosity, but one is much cooler than the other, then the cool star must have a much larger radius to compensate. And that is exactly what we see with red supergiants. They are extremely luminous, maybe a few 100,000 times the luminosity of the Sun, but they are very cool, with surface temperatures of only about 3,000 to 3,500 Kelvin. To produce that much luminosity at such a low temperature, they must have enormous radii. The math demands it. And this is, in fact, one of the primary ways that astronomers calculate the radii of distant stars. They measure the luminosity and the temperature, plug them into the Stephenson-Boltzmann law, and solve for the radius. We will return to the details and challenges of this method later in our journey. But for now, remember this equation, because it is the key to understanding why the biggest stars are red, why they are cool, and why their size is so extreme. Now I want to take you on a journey through the classification of stars, because this is the framework that astronomers use to organize the stellar zoo, and it will help us understand exactly where our colossal stars fit in the grand scheme of things. In the early 20th century, astronomers at Harvard College Observatory, most of them women who were at the time referred to as human computers because they were paid to analyze photographic plates of stellar spectra, developed a system for classifying stars based on the patterns of dark lines in their spectra. These dark lines, called absorption lines, are caused by specific elements in the star's atmosphere absorbing specific wavelengths of light. Different elements absorb different wavelengths, so the pattern of absorption lines acts like a fingerprint, revealing the star's chemical composition and, crucially, its temperature. The classification system that emerged from this work sorts stars into 7 main spectral types, designated by the letters O, B, A, F, G, K, and M. There is a famous mnemonic for remembering this sequence: "Oh be a fine guy, kiss me," or "Oh be a fine girl, kiss me," depending on your preference. The sequence runs from the hottest stars to the coolest. O-type stars are the hottest, with surface temperatures above 30,000 Kelvin. They glow with a fierce blue light and are extremely rare, making up less than 1% of all stars. They are also the most massive and most luminous stars on the main sequence. B-type stars are slightly cooler, between about 10,000 and 30,000 Kelvin, blue-white in colour and still very luminous. Type stars between about 7,500 and 10,000 Kelvin are white and include some of the most famous stars in the sky, like Sirius and Vega. F-type stars between about 6,000 and 7,500 Kelvin are yellow-white. G-type stars between about 5,200 and 6,000 Kelvin are yellow, and this is where our Sun lives. Our Sun is classified as a G2V star, a fairly ordinary yellow dwarf. K-type stars between about 3,700 and 5,200 Kelvin are orange. And finally, M-type stars with temperatures below about 3,700 Kelvin are the coolest, glowing with a deep red light. M-type stars are by far the most common, making up about 70 to 80% of all stars in the galaxy. Most of them are small, dim, long-lived red dwarfs, but some of them, the ones at the extreme upper end of the luminosity scale, are something else entirely. They are the red supergiants and red hypergiants, the very stars we are hunting. And here is the key insight. Every single one of the candidates for the biggest star in the universe, every single one is an M-type star. They all glow red, they are all cool, and they are all dying. In addition to the spectral type, stars are also assigned a luminosity class, which indicates their intrinsic brightness and physical size. The system uses Roman numerals, with Ia plus or 0 designating the most luminous hypergiants, Ia for luminous supergiants, Ib for less luminous supergiants, 2 for bright giants, 3 for normal giants, 4 for subgiants, 5 for main sequence stars, also called dwarfs, and so on down to white dwarfs. When you put the spectral type and luminosity class together, you get a complete stellar classification. Our Sun is G2V, meaning it is a G-type star, subtype 2, on the main sequence. Betelgeuse, the famous red supergiant in the constellation Orion, is classified as M1 to M2 Ia to Iab, meaning it is a cool M-type star with supergiant luminosity. And the biggest stars, the ones we are searching for, are classified as M-type, with luminosity class Ia+, the hypergiant designation, or Ia, the luminous supergiant designation. They occupy the extreme upper right corner of one of the most important diagrams in all of science. A diagram that we need to discuss now, because it is the single most powerful tool astronomers have for understanding stellar life and death. This diagram is called the Hertzsprung-Russell diagram, or HR diagram for short. It was developed independently by two astronomers in the early 20th century, Einar Hertzsprung of Denmark and Henry Norris Russell of the United States. What they did was plot stars on a graph with two axes. The horizontal axis represents the surface temperature of the star, and by convention, it runs from hot on the left to cool on the right. The vertical axis represents the luminosity of the star, running from dim at the bottom to bright at the top. Now, if stars had random properties, you would expect them to scatter randomly across this diagram. But when Hertzsprung and Russell plotted real stars, they found that the points were not random. They fell into distinct, well-defined groups. The most prominent feature is a broad diagonal band running from the upper left, where the hottest and most luminous stars live, to the lower right, where the coolest and dimmest stars reside. This band is the main sequence, and it contains the vast majority of all stars, including our Sun. Stars on the main sequence are in the prime of their lives, steadily fusing hydrogen in their cores. Above and to the right of the main sequence, there is a region occupied by giant and supergiant stars. These are the evolved stars, the ones that have left the main sequence and expanded into giants or supergiants. They are cool but very luminous, which means they must be very large. And at the very top of this region, in the extreme upper right corner, are the red supergiants and hypergiants, the biggest stars. the ones with surface temperatures below 4,000 Kelvin and luminosities hundreds of thousands of times greater than the Sun. This corner of the HR diagram is the VIP section of the stellar world. Only the most extreme, most evolved, most enormous stars get to sit here, and every star that enters this region is on borrowed time. Below the main sequence, in the lower left, is a region occupied by white dwarfs, the dense, hot, fading remnants of dead stars. These are the corpses of stars that were once on the main sequence, stars like our Sun that have exhausted their fuel and shed their outer layers, leaving behind a small, incredibly dense core about the size of Earth, but with the mass of the Sun. The HR diagram is not just a static snapshot. It is a map of stellar evolution. Stars do not remain in one place on this diagram. They move, tracing paths across the diagram as they age and evolve. A massive star, when it is first born, appears on the upper main sequence, in the hot, blue, luminous region on the upper left. It spends millions of years there, steadily burning hydrogen. But when the core hydrogen runs out, the star begins to evolve. It moves to the right on the HR diagram, meaning it is cooling down and expanding. It enters the giant region, then the supergent region. If the star is massive enough, it keeps going, further and further to the right, expanding to larger and larger radii, its surface temperature dropping lower and lower until it reaches the extreme upper right corner, the red supergent zone, and there it sits, bloated and unstable, shedding mass, pulsating erratically, waiting for its core to finally collapse. This journey from the upper left to the upper right of the HR diagram is the story of a massive star's life and death. It is a journey that takes only a few million years for the most massive stars, a blink of an eye in cosmic terms. And it ends, always, in spectacular fashion. But there is a limit. The HR diagram has a boundary on the right side, a line that stars cannot cross while remaining stable. This boundary is called the Hayashi limit, or the Hayashi track, named after Japanese astrophysicist Chushiro Hayashi, who first described it in 1961. The Hayashi limit represents the maximum radius, or equivalently the minimum surface temperature, that a star of a given mass can have while still maintaining hydrostatic equilibrium. In other words, there is a point beyond which a star simply cannot expand any further. If it tries to cool below the Hayashi limit temperature, its outer layers become fully convective, meaning energy is transported entirely by churning motions of gas rather than by radiation, and the star becomes unstable. It can no longer maintain its structure. Its outer layers would be ejected into space, or the star would oscillate wildly. For red supergiants in our galaxy, the Hayashi limit corresponds to a surface temperature of roughly 3,500 Kelvin and a radius of roughly 1,500 solar radii. This number, 1,500 solar radii, is incredibly important. It is, in a sense, the speed limit of the stellar size universe, the theoretical maximum radius that a star can achieve while remaining a recognizable, coherent star. And as we will see, the largest stars we have measured cluster remarkably close to this limit. Some appear to exceed it, which raises deep questions about either our measurements or our theories. We will explore this tension in great detail as we continue our journey. Now let us begin climbing the size ladder. Let us start small and work our way up, step by step, to the most colossal stars ever found. And with each step, I want you to try to feel the scale, to sense just how dramatically the dimensions change as we ascend from dwarf stars to hypergiants. At the bottom of the ladder are the red dwarfs. These are the smallest true stars, the ones that are just barely massive enough to sustain hydrogen fusion in their cores. The smallest red dwarfs have radii of about 0.1 solar radii, meaning they are about 10% the size of our Sun. That is roughly the size of Jupiter. In fact, some red dwarfs are barely distinguishable from giant planets in terms of their physical size. The difference is that they are far denser and far hotter at their cores, allowing fusion to occur. Proxima Centauri, the closest star to our Sun at about 4.24 light-years away, is a red dwarf with a radius of about 0.15 solar radii. It is a tiny, dim, reddish star that you cannot even see with the naked eye despite being our nearest stellar neighbour. But red dwarfs are the most common type of star in the universe, making up roughly 70 to 80% of all stars. They are also the longest lived. Because they burn their fuel so slowly, red dwarfs can survive for trillions of years, far longer than the current age of the universe, which is only about 13.8 billion years. No red dwarf that has ever been born has yet died of old age. They are the slow, steady, patient members of the stellar family. One step up the ladder, we find our own Sun. The Sun has a radius of about 696,000 kilometers, or one solar radius by definition. Its diameter is about 1.4 million kilometers. To put this in perspective, you could line up 109 Earths across the face of the Sun. Or you could fit about 1.3 million Earths inside the Sun's volume. The Sun is a G2V star, a yellow dwarf, middle-aged at about 4.6 billion years old, with a surface temperature of about 5,778 Kelvin. It is, by cosmic standards, completely unremarkable. Average in mass, average in temperature, average in luminosity, average in size. But it is perfect for us. Its steady, moderate output of energy has allowed life to develop and flourish on Earth for billions of years. In the grand scheme of what we are about to discuss, however, the Sun is tiny. It is the measuring stick we will use, but it is not even close to the stars we are heading toward. Moving further up, we encounter stars like Pollux, a bright orange star in the constellation Gemini. Pollux is a giant star with a radius of about 9 solar radii, meaning it is 9 times wider than our Sun. It has moved off the main sequence and begun to expand as it evolves toward the end of its life. Still impressive by human standards, but tiny compared to what is coming. A bit further up, we find Arcturus, one of the brightest stars in the night sky, a red giant in the constellation Bootes. Arcturus has a radius of about 25 solar radii. It is 25 times wider than the Sun, which means its diameter is about 35 million kilometers. If Arcturus were placed where the Sun is, it would extend about halfway to the orbit of Mercury. This is starting to get serious. Continuing up the ladder, we reach the realm of bright giants and supergiants. Canopus, the second brightest star in the night sky, is a bright giant or supergiant with a radius of about 71 solar radii. Rigel, the brilliant blue-white star in Orion, is a blue supergiant with a radius of about 78 solar radii. These are genuinely enormous stars, dozens of times wider than the Sun. But notice something important. Both Canopus and Rigel are hot stars. They are blue or white, they have high surface temperatures, and because they are hot, they are relatively compact for their luminosity. They have not yet expanded into the red supergent phase. Their enormous luminosity comes from their extreme temperature, not from extreme size. The truly enormous stars by radius are the ones that have expanded and cooled, the red ones. And so, we arrive at the red supergent realm. This is where the sizes become truly staggering. Let us start with the most famous red supergent of all, Betelgeuse. Betelgeuse is the bright orange-red star marking the left shoulder of Orion the Hunter. It is one of the brightest stars in the night sky, and it is visible to the naked eye from virtually anywhere on Earth. Betelgeuse is classified as an M-type supergent, with a surface temperature of about 3,500 Kelvin. Its distance is approximately 650 light-years from Earth, and its radius is estimated to be somewhere between 700 and about 1,000 solar radii, depending on the measurement and the wavelength of observation. This range is not because astronomers cannot make up their minds. It is because Betelgeuse is a semi-regular variable star. It pulsates. Its outer atmosphere expands and contracts over periods of about 400 days for its primary pulsation, and about 2,100 days for a secondary longer period. During these pulsations, its radius can change by a significant fraction. It literally breathes. When Betelgeuse is at its average size of about 700 to 800 solar radii, if you placed it where the Sun is, its surface would extend past the orbit of Mars, reaching roughly to the asteroid belt between Mars and Jupiter. When it is at its maximum extent, during a pulsation peak, it might reach even further, possibly approaching Jupiter's orbit. Betelgeuse is a dying star, expected to explode as a supernova within the next 100,000 years or so, though the exact timing is unknown. It could be tomorrow. It could be in 100,000 years. When it does explode, it will briefly become as bright as the full moon in our sky, visible even during the day, before fading over weeks and months. It was Betelgeuse that captured the world's attention in late 2019 and early 2020 when it underwent what has been called the Great Dimming. The star's brightness dropped dramatically over a period of months, leading to widespread speculation that it might be about to go supernova. Astronomers and the public alike were riveted. Was Betelgeuse about to explode? Were we about to witness one of the most spectacular astronomical events in human history? The answer, as it turned out, was no. Subsequent observations revealed that the dimming was caused by two simultaneous events: a large blob of cooler gas on the star's surface, reducing its luminosity from that region, and a cloud of dust that Betelgeuse had recently ejected into space, which partially blocked our view of the star. The Great Dimming was not a prelude to a supernova. It was simply a reminder of how dynamic, how active, how alive these massive stars truly are. They are not static objects. They churn, they pulsate, they erupt, they shed material. They are constantly changing, constantly evolving, on timescales that we can actually observe within a human lifetime. Betelgeuse, at 700 to 1,000 solar radii, is enormous, but it is not even close to the top of the size ladder. Because above the red supergiants are the red hypergiants, the extreme supergiants, the stars that push the boundaries of what is physically possible. And it is in this rarefied category that we find the candidates for the most colossal star ever identified. Let me introduce them to you one by one in ascending order of their claimed or estimated size. First, let me take you to the constellation Canis Major, the Great Dog. There, about 3,900 light-years from Earth, burns a star called Canis Majoris. For decades, Canis Majoris was the answer to the question, what is the biggest star? It appeared in textbooks, documentaries, classroom posters, and popular science articles as the undisputed champion of stellar size. And even though it has since been surpassed by other candidates, it remains one of the most extraordinary and well-studied stars in the entire sky. Canis Majoris is classified as a red supergiant or hypergiant, with a spectral type of M3 to M4.5. Its surface temperature is about 3,490 degrees Celsius, or approximately 3,730 Kelvin. Its luminosity is estimated at around 270,000 to 500,000 times the luminosity of the Sun. And its radius is currently estimated at about 1,420 solar radii, 1,420 times the width of our Sun. To visualize this, imagine placing Canis Majoris at the center of our solar system, where the Sun sits now. Mercury, at about 0.4 astronomical units from the Sun, would be deep inside the star. Venus at 0.7 AU, gone. Earth at 1 AU, consumed. Mars at 1.5 AU, engulfed. The asteroid belt at 2 to 3.5 AU, buried deep within the stellar atmosphere. Jupiter at 5.2 AU, still inside the star. And the star's surface would extend to about 6.6 AU, meaning it would reach well past Jupiter and most of the way to Saturn's orbit. If you were travelling at the speed of light, it would take you about 6 hours to circumnavigate this star. 6 hours at 300,000 kilometers per second. If you were flying a commercial aircraft at 900 kilometers per hour, the trip around Canis Majoris would take approximately 700 years. 7 centuries of non-stop flying just to go around it once. But Canis Majoris is not just remarkable for its size, it is remarkable for what it is doing to itself. This star is one of the most extreme mass-losing objects in the entire galaxy. It is literally tearing itself apart. Observations from the Hubble Space Telescope and ground-based observatories have revealed a complex, asymmetric nebula surrounding Canis Majoris, composed of arcs, knots, filaments, and plumes of ejected material. The star is shedding mass at a rate of approximately 30 Earth masses per year, 30 times the mass of our entire planet ejected into space every single year. This is not a gentle process. The mass loss is not smooth or uniform. It comes in episodes, in violent eruptions that fling enormous quantities of material outward. Some of these eruptions may be caused by massive convective cells on the star's surface. Convection cells on our Sun are about 1,000 kilometers across and are responsible for the granulated appearance of the solar surface. On Canis Majoris, these convective cells could be hundreds of millions of kilometers across, bigger than the orbit of Earth. When one of these cells erupts, it can launch a plume of gas and dust outward at speeds of tens of kilometers per second, creating the complex nebula structures that Hubble has imaged. The material ejected by Canis Majoris over millions of years has formed a thick, dusty shell around the star, obscuring it at visible wavelengths but making it glow brightly in infrared. In fact, Canis Majoris is one of the brightest infrared sources in the sky, and all of this ejected material, all of this stellar debris, will eventually be incorporated into new generations of stars and planets, seeding the interstellar medium with heavy elements that were forged in Canis Majoris' core and envelope. When Canis Majoris finally dies, most likely within the next few 100,000 years, it will explode as a supernova, adding even more material to this cosmic recycling process. The remnant core will almost certainly collapse into a black hole, given the star's enormous mass. Canis Majoris held the title of largest known star for many years, but in 2012, a new measurement challenged its reign and thrust a different star into the spotlight. That star is Scuti, and its story is one of the most fascinating and contentious in modern astronomy. Scuti is located in the constellation Scutum, the Shield, approximately 9,500 light-years from Earth, much closer to the center of the Milky Way galaxy than we are. It was first catalogued in 1860 by German astronomers at the Bonn Observatory, who noticed it as a variable star, meaning its brightness changes over time. But its true nature was not appreciated for over a century. In 2012, a team of astronomers led by Arroyo Torres used the Very Large Telescope Interferometer, the VLTI, located in the Atacama Desert of Chile, to directly measure the angular diameter of Scuti. They combined this angular measurement with a distance estimate to calculate the physical radius of the star, and the number they got was astonishing. 1,708 solar radii, with an uncertainty of plus or minus 192. This was, at the time, the largest stellar radius ever measured, surpassing Canis Majoris by a wide margin. At 1,708 solar radii, Scuti would have a diameter of about 2.4 billion kilometers. If placed at the center of our solar system, its photosphere, its visible surface, would extend beyond the orbit of Jupiter at 5.2 AU and approach or reach the orbit of Saturn at 9.5 AU. Light would take about 2 hours and 13 minutes to travel across its diameter. A commercial aeroplane would need over 1,100 years to fly around it. The news spread rapidly through the astronomy community and the popular media. Scuti was declared the biggest star in the universe, and for several years that title stuck. But there were problems. Significant problems, and as time went on and more astronomers scrutinized the data, the cracks in Scuti's claim began to show. The first issue was the uncertainty in the measurement itself. plus or minus 192 solar radii is a massive error bar. It means the true radius could be anywhere from about 1500 to 1900 solar radii. That is a huge range. The second and more serious issue was the distance. Scuti is located near the galactic center, in a region of the sky that is heavily obscured by interstellar dust. Dust absorbs and scatters starlight, making stars appear dimmer and redder than they actually are. To determine Scuti's true luminosity, astronomers need to correct for this dust extinction. But estimating the amount of dust along the line of sight to a star 9,500 light-years away in one of the dustiest regions of the galaxy is extraordinarily difficult. Small errors in the extinction correction translate to large errors in the luminosity, which in turn propagate to large errors in the radius calculation via the Stefan-Boltzmann law. The third issue was the distance estimate itself. Getting an accurate distance to a star that far away, especially one obscured by dust, is extremely challenging. Different methods and different studies have yielded different distances, and each different distance gives a different radius. As more refined measurements and analyses were carried out in subsequent years, the estimated radius of Scuti began to shrink. Some studies placed it closer to 750 to 900 solar radii. The most recent assessments suggest a radius of approximately 909 solar radii. Still enormous, still mind-boggling, still hundreds of times larger than our Sun, but far from the original claim of 1,708. Scuti likely is not the largest known star. Its original measurement was an overestimate, inflated by uncertainties in distance and dust correction. The story of Scuti is an important lesson in the nature of scientific measurement. When you are dealing with objects at the extreme edge of human observation, objects that are thousands of light-years away, obscured by dust, pulsating irregularly and surrounded by complex mass-loss environments, getting an accurate measurement is one of the hardest things in all of science. The uncertainty is not a failure of the scientists. It is an inherent property of the measurement. And it means that the title of biggest star is not a permanent fixed crown. It is a provisional designation, subject to change as our instruments improve, our methods are refined, and new data come in. The biggest star today may not be the biggest star tomorrow. And the biggest star tomorrow may turn out to be a star we have not even measured yet. Let me now introduce you to a star whose name sounds more like a galactic address than a stellar designation. Stephenson 218, also known as Stephenson 2 DFK1 or STEAT 2-18. This star is associated with, or at least located near, a massive open cluster called Stephenson 2, which was discovered in 1990 by American astronomer Charles Bruce Stephenson while analyzing data from a deep infrared survey. The cluster, also known as RSGC2, Red Supergiant Cluster 2, is located in the constellation Scutum, approximately 19,000 light-years from Earth, in the Scutum-Centaurus arm of the Milky Way galaxy. This cluster is remarkable because it contains a high concentration of red supergiants, a rare and significant grouping of dying massive stars. Stephenson 2-18 is the brightest star in the region of this cluster, though its actual membership in the cluster is the subject of ongoing scientific debate. The story of Stephenson 2-18's size begins with a 2012 study by Thomas and collaborators who used the dusty model to fit the star's spectral energy distribution, the pattern of how much energy the star emits at different wavelengths. From this fitting, they derived a bolometric luminosity of approximately 440,000 solar luminosities and an effective temperature of approximately 3,200 Kelvin. When you plug these numbers into the Stefan-Boltzmann law and solve for the radius, you get a staggering result. Approximately 2,150 solar radii, 2,150 times the width of our Sun. If this number is correct, Stephenson 2-18 is not just the largest known star. It is far larger than any other measured star, and it significantly exceeds the theoretical Hayashi limit of about 1,500 solar radii. At 2,150 solar radii, the star's diameter would be approximately 3 billion kilometers, or about 10 astronomical units. Placed at the center of our solar system, its surface would extend past the orbit of Saturn at 9.5 AU, reaching almost to the orbit of Uranus. Light would need almost 3 hours to cross it. The volume would be approximately 10 billion times that of our Sun. It is a number so large that it almost defies comprehension. But this measurement is deeply controversial, and there are several reasons to treat the 2150 solar radii figure with extreme caution. The first issue is the effective temperature. 3200 Kelvin is significantly below the Hayashi limit for red supergiants, which is typically around 3500 Kelvin. A star with a surface temperature below the Hayashi limit would not be in hydrostatic equilibrium. It would be unstable. Its outer layers would be falling apart or being ejected. Now, it is possible that Stephenson 218 genuinely is below the Hayashi limit and is in the process of losing its outer layers. But it is also possible, and perhaps more likely, that the temperature measurement is wrong, biased by the complex dust environment around the star or by uncertainties in the model used to fit the spectral energy distribution. If the true temperature is higher, say 3500 Kelvin, instead of 3200, then the radius calculation would give a significantly smaller number. The second issue is the distance. Stephenson 218's distance is inferred from its assumed association with the Stephenson 2 cluster, which has a kinematic distance of about 5.8 kiloparsecs, or roughly 19,000 light-years. But Stephenson 218's membership in this cluster is far from certain. Its radial velocity, the speed at which it is moving toward or away from us, is about 89 kilometers per second. The average radial velocity of the other stars in Stephenson 2 is about 109 kilometers per second. This is a significant discrepancy, and it has led some astronomers to conclude that Stephenson 218 is not actually a member of the cluster at all, but rather a foreground star, a red supergiant that just happens to lie in the same direction on the sky, but is at a completely different distance. If the star is at a different distance, then its luminosity and therefore its radius could be very different from the published values. The distance uncertainty has been stated to be greater than 50%, meaning the star could be anywhere from about 9,000 to 28,000 light-years away. That is an enormous range, and it translates to a correspondingly enormous range of possible radii. The third issue is the spectral energy distribution itself. A more recent analysis by Humphreys and collaborators in 2020, using spectral energy distribution integration based on published flux measurements and assuming the same distance of 5.8 kiloparsecs, derived a bolometric luminosity of 630,000 solar luminosities, significantly higher than the earlier estimate. But they also noted that the SED of Stephenson 218 is peculiar and cannot be fitted to standard reddening laws. This implies that the star has higher extinction than expected, which in turn implies that it may be even more luminous than the 630,000 figure suggests. However, this peculiarity also raises the possibility that the star's properties are not well characterized, and that the derived radius may be unreliable. So where does this leave us? Stephenson 218 remains a fascinating and tantalizing object. If its claimed radius of 2,150 solar radii is correct, it is by far the largest star ever measured, exceeding the Hayashi limit and challenging our understanding of stellar structure. But the evidence is uncertain. The temperature may be wrong, the distance may be wrong, the cluster membership may be wrong, and until these uncertainties are resolved, the 2,150 figure must be treated as an upper limit or a speculative estimate rather than a firm measurement. Many astronomers are cautious about accepting it at face value, and there is a growing consensus that the true radius is likely smaller, probably closer to the Hayashi limit of around 1,500 solar radii or less. This brings us to a star that many astronomers now consider the strongest candidate for the title of largest reliably measured star. a star that is not even in our galaxy. A star that resides 163,000 light-years away in a small companion galaxy orbiting the Milky Way. That star is WOH G64, and its story is one of the most remarkable in stellar astronomy. WOH G64 is located in the Large Magellanic Cloud, abbreviated LMC, which is a satellite galaxy of the Milky Way visible from the southern hemisphere as a faint, fuzzy patch of light in the constellation Dorado. The LMC is one of the closest galaxies to our own, at a well-established distance of approximately 163,000 light-years. This well-known distance is crucial because it eliminates one of the largest sources of uncertainty that plagues measurements of stars within the Milky Way. When you know the distance with high confidence, you can calculate the luminosity with high confidence, and from there the radius becomes much more reliable. WOH G64 gets its name from its discoverers, Westerlund, Olander, and Hedin, who catalogued it as part of their survey of red stars in the Magellanic Clouds. It is classified as a red supergent with a spectral type of M5. Its mass is estimated at approximately 20 solar masses. Its luminosity is approximately 282,000 solar luminosities. Its surface temperature is approximately 3,400 Kelvin, or about 3,100 degrees Celsius, which is considerably cooler than our Sun's 5,500 degrees Celsius, but typical for a red supergiant. And its estimated radius is approximately 1,540 solar radii. Let me pause here and let that number settle in. 1,540 solar radii. That means WOH G64 is 1,540 times wider than our Sun. Its diameter is approximately 2.14 billion kilometers, or about 14.3 astronomical units. If you placed WOH G64 at the center of our solar system, Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all be deep inside the star. Saturn, orbiting at 9.5 AU, would be inside the star. The surface of WOH G64 would extend to about 7.15 AU from its center. Wait, let me recalculate that more carefully. 1,540 solar radii means the radius is 1,540 times 696,000 kilometers, which is approximately 1.07 billion kilometers, or about 7.16 AU. So the surface would be at about 7.16 AU from the center. Jupiter is at 5.2 AU, so it would be well inside the star. Saturn is at 9.5 AU, so it would actually be outside the star's photosphere, but not by much. The point is that this star is so large that it would engulf most of our solar system. Everything out to about 70% of the way to Saturn would be inside this single stellar object. What makes WOH G64's measurement particularly compelling is the method used. Observations were conducted with the VLT using the gravity instrument, which combines light from the 48.2-meter telescopes of the Very Large Telescope at infrared wavelengths between 2.0 and 2.45 micrometers. With a maximum projected baseline length of 129 meters, the gravity instrument was able to directly constrain the angular size of WOH G64. Combined with the well-known distance to the LMC, this gave a robust physical radius estimate. This is about as reliable as stellar size measurements get. The distance is known. The angular size is directly measured. The temperature is constrained by spectral analysis. The radius follows from straightforward physics. There are still uncertainties, of course. The star's extended, dusty atmosphere makes the boundaries somewhat fuzzy. Different wavelengths probe different atmospheric layers, giving slightly different apparent sizes. But compared to the enormous uncertainties associated with Stephenson 218 or UI Scuti, WOH G64's measurement is on much firmer ground. But there is another reason why WOH G64 has captured the attention of astronomers in recent years, and it goes beyond mere size. Recent observations have revealed that WOH G64 appears to be changing. It is not static, it is evolving, possibly transitioning from one state to another right before our eyes. The star is embedded in a thick, dusty torus, a ring of material that it has ejected over time. This torus extends roughly 1 light year in diameter, an enormous cocoon of dust and gas surrounding the dying star. And recent VLT gravity observations from 2024 have found evidence that the star's appearance has changed compared to earlier observations. The details are still being analysed and debated, but the implication is profound. We may be watching a supergent star undergo an evolutionary transition in real time. This could be an episode of extreme mass loss, a change in the star's spectral type, or even the beginning of the end, the first signs of the star's approach to its final collapse. Whatever the explanation, it reinforces the fact that these colossal stars are not stable, eternal objects. They are dynamic, turbulent, restless beings, constantly changing, constantly evolving, and constantly reminding us that the universe is not static. It is a living, breathing, ever-changing cosmos. Now, there is one more candidate that I want to introduce you to, a star that has emerged relatively recently in the conversation about the largest known stars. Its name is RSGC1-FO1, and it is located in another massive star cluster in the constellation Scutum, the Red Supergent Cluster 1, or RSGC1. This cluster, like Stephenson 2, is a dense concentration of red supergents in the Scutum-Centaurus arm of the Milky Way. RSGC1-FO1 has an estimated radius of between 1,436 and 1,530 solar radii, putting it in the same size range as WOH G64 and making it one of the largest stars reliably measured within our own galaxy. It is a red supergiant, like all the other contenders, and it sits within a cluster whose distance can be estimated from the collective properties of its member stars. While RSGC1-FO1 has not received as much popular attention as Canis Majoris or Scuti, it is increasingly recognized as a top-tier candidate for the largest star in the Milky Way. And there are others. HV888, also known as WOH 140, is a red supergiant in the Large Magellanic Cloud, with an estimated radius of approximately 1,470, 7 to 1,509 solar radii. HD 269551a is another LMC red supergiant, with a radius of approximately 1,439 solar radii. WOH S170, also in the LMC, comes in at about 1,461 solar radii. HD 1463, also in the LMC, has a radius of approximately 1,420 solar radii. R Scorpii, a red supergiant in our own galaxy in the constellation Scorpius, has a radius of approximately 1,411 solar radii. CM Velorum in the constellation Vela is estimated at about 1,416 solar radii. These are all immense stars, all hovering around the 1,400 to 1,500 solar radii range. They cluster remarkably close to the theoretical Hayashi limit of about 1,500 solar radii for Milky Way metallicity stars. This clustering is not a coincidence. It is a reflection of the underlying physics. Red supergiants expand until they approach the Hayashi limit, where their outer layers become unstable. They cannot easily grow beyond this limit, so the largest stars naturally pile up near it, like water rising to the brim of a glass, but not easily overflowing. So let me now try to give you a clear, honest answer to the question we have been building toward throughout this entire journey. What is the most colossal star we have ever identified in the cosmos? The answer depends on how you define the question. If you are asking about the largest claimed radius, the answer is Stephenson 218 at approximately 2,150 solar radii, but this measurement is highly uncertain and possibly unreliable. If you are asking about the largest reliably measured radius, the answer is WOH G64 at approximately 1,540 solar radii. This measurement benefits from a well-known distance, direct interferometric angular size constraints, and good spectral data. If you are asking about the largest well-measured star in the Milky Way, the answer is a close contest between RSGC-1-F01 at 1,436 to 1,530 solar radii and Canis Majoris at approximately 1,420 solar radii. And if you are asking about the most famous star to have held the title, many people would say WOH Scuti, though its original measurement of 1,708 solar radii has been revised downward to approximately 909 solar radii. The honest truth is that the question does not have a single, definitive answer, and that in itself tells us something profound about the nature of science. Science does not always give us neat, clean, final answers. Sometimes the answer is, it depends. Sometimes the answer is, we are not sure yet. And that is not a weakness. That is the strength of science. It is the honest acknowledgement that our knowledge is always provisional, always subject to revision, always open to new data and new understanding. The biggest star today may not be the biggest star tomorrow. A new survey may discover a previously unknown supergiant hiding behind a cloud of dust in some unexplored corner of the galaxy. A revised distance measurement may inflate or deflate the size of a current candidate. A new theoretical model may change our understanding of the Hayashi limit, allowing for larger or smaller maximum radii. The quest for the biggest star is not a finished story. It is an ongoing adventure. And that is what makes it so exciting. Now I want to take some time to discuss in depth how astronomers actually go about measuring the sizes of stars that are thousands or even hundreds of thousands of light years away. Because this is not obvious. You cannot fly to a star with a ruler, you cannot wrap a measuring tape around it, and even with the most powerful telescopes. Most stars are so far away that they appear as nothing more than points of light, mere dots with no discernible size. So how do we do it? How do we take a dot of light thousands of light years away and determine that it is 1,540 times wider than our Sun? The answer involves some of the most ingenious techniques in all of observational science, and it also involves accepting a degree of uncertainty that would make most people uncomfortable. The first and most fundamental method is the one we have already discussed, the Stefan-Boltzmann law. If you know a star's luminosity and its effective surface temperature, you can calculate its radius. This is the workhorse method used for the vast majority of stellar radius estimates. But as we discussed, it requires three pieces of information, each of which has its own uncertainties. You need the luminosity, which requires knowing the distance and the apparent brightness, and correcting for interstellar dust absorption. You need the temperature, which requires analysing the star's spectrum and fitting it to theoretical models. And you need the Stefan-Boltzmann constant and the mathematical framework of blackbody radiation, which thankfully are very well established. The challenges lie entirely in the observational inputs, distance, apparent brightness, dust correction, and spectral analysis. Let me walk you through each of these in more detail, because the devil truly is in the details. Start with distance. For nearby stars within a few hundred or perhaps a couple of thousand light years, we can measure distances using a technique called parallax. Parallax exploits the fact that as the Earth orbits the Sun, our viewing angle to a star changes slightly over the course of a year. A nearby star appears to shift back and forth against the background of more distant stars, tracing out a tiny ellipse on the sky. The size of this ellipse, measured as an angle, is inversely proportional to the star's distance. A star at 1 parsec, about 3.26 light years, would have a parallax angle of 1 arcsecond, hence the name parsec, a contraction of parallax arcsecond. The European Space Agency's Gaia spacecraft, launched in 2013, has measured parallaxes for nearly 2 billion stars with unprecedented precision. For many of the stars we have discussed, Gaia provides the best available distance estimates. However, for the most distant and most dust-obscured stars, like many of our supergiant candidates deep in the galactic plane, even Gaia's parallaxes become unreliable, because the parallax angle is so tiny that it is comparable to the measurement uncertainty. For these stars, distances are estimated through other methods. One common approach is to assume the star is a member of a known cluster whose distance has been independently determined. If you know the distance to the cluster, and you have reason to believe the star is a member of the cluster, you assign the cluster's distance to the star. But as we saw with Stephenson 218, cluster membership can be uncertain, and an incorrect assumption about membership can lead to wildly incorrect distances. Another approach is to use kinematic distances, which exploit the known rotation pattern of the Milky Way galaxy. If you measure a star's radial velocity from the Doppler shift of its spectral lines, you can use the rotation curve of the galaxy to estimate how far away the star is. This works reasonably well on average, but can have large uncertainties for individual stars, especially in complex regions near the galactic center, where the simple rotation model breaks down. For stars in external galaxies like the Large Magellanic Cloud, the distance problem is largely solved. The LMC's distance has been measured to high precision using multiple independent methods, including Cepheid variable stars, eclipsing binaries, and the tip of the red giant branch. The current best estimate is about 163,000 light-years, with an uncertainty of only a few %. This is why measurements of stars in the LMC, like WOH G64, are considered more reliable than measurements of similarly obscured stars within our own galaxy. Next, apparent brightness and dust correction. The apparent brightness of a star is measured using photometry, the precise measurement of how much light we receive from the star at various wavelengths. Modern photometry is extremely precise, capable of measuring brightnesses to within a fraction of a %. The challenge comes from interstellar dust. Dust grains between us and the star scatter and absorb starlight, making the star appear dimmer and redder than it actually is. This effect is called interstellar extinction, and it can be very large for stars in the galactic plane, especially near the galactic center. Correcting for extinction requires estimating the amount of dust along the line of sight, which is done using empirical reddening maps, measurements of the reddening of other stars in the same direction, or modeling of the interstellar medium. The uncertainty in extinction correction is often the dominant source of error in luminosity calculations for dusty, distant stars. For some stars, the extinction can be uncertain by several tenths of a magnitude or more, which translates to uncertainties of tens of % in luminosity, which in turn translates to uncertainties of 10 to 20% in radius. Then there is the temperature. For most stars on the main sequence, temperatures are well determined from spectral analysis. But for cool red supergiants, things get complicated. Their atmospheres are extended, tenuous, and complex, often containing molecular bands of titanium oxide, vanadium oxide, and carbon monoxide that dramatically affect the spectrum. Different models for fitting these spectra can yield different temperatures. The pulsating nature of many red supergiants means the temperature is not even constant. It changes over time as the star expands and contracts. And the extended atmosphere means that the concept of a single, well-defined surface temperature is somewhat fuzzy. The effective temperature of a red supergiant is more of an average, a summary statistic that captures the overall thermal state of the star's radiating surface, but does not fully describe the complexity of the three-dimensional, time-varying atmosphere. All of these factors contribute to typical temperature uncertainties of 200 to 500 Kelvin for red supergiants. And because temperature appears to the fourth power in the Stefan-Boltzmann law, even a relatively small uncertainty in temperature can have a large impact on the derived radius. If you think the temperature is 3200 Kelvin, but it is actually 3500 Kelvin, your radius estimate will be off by about 25%. That is the difference between a star being 1500 solar radii or 2000 solar radii. This is exactly what likely happened with Stephenson 218. An underestimate of the temperature led to an overestimate of the radius. The second major method for measuring stellar sizes is stellar interferometry, which I mentioned earlier. This is the gold standard. the most direct and least model-dependent method available. Let me explain it in a bit more detail, because it is truly a remarkable feat of human ingenuity. The fundamental idea is based on the wave nature of light. When light from a distant star enters two separated telescopes, the light waves travel slightly different paths to reach the two instruments. The difference in path length depends on the direction of the star and the separation, or baseline, between the telescopes. By combining the light from the two telescopes and analysing the resulting interference pattern, the pattern of bright and dark fringes created by the constructive and destructive interference of the waves, astronomers can extract information about the angular size of the source. For a point source, a perfectly unresolved star, the interference fringes have maximum contrast. The bright fringes are very bright and the dark fringes are very dark. But for an extended source, a star with a measurable angular diameter, the light from different parts of the stellar disk follows slightly different paths, and the fringes become blurred. The contrast decreases. By measuring how the fringe contrast or visibility changes as a function of the baseline length, astronomers can determine the angular diameter of the star. The longer the baseline, the smaller the angular size that can be resolved. The Very Large Telescope Interferometer, with baselines up to about 130 meters, can resolve angular diameters as small as a few milliarcseconds. For reference, 1 arcsecond is 1/3600th of a degree. 1 milliarcsecond is 1,000th of an arcsecond. To give you a sense of how small this is, it is equivalent to the angular size of a coin on the surface of the Moon as seen from Earth. Wilty can measure stellar disks smaller than this. It is an almost inconceivable level of precision. But even interferometry has its limitations. The measurement depends on the wavelength of observation, because the star's atmosphere is not opaque at all wavelengths. At shorter wavelengths you see deeper into the atmosphere, where the star appears smaller. At longer wavelengths the opacity increases, and you see the outer, more extended layers, making the star appear larger. So the measured angular diameter is wavelength dependent, and converting it to a physical radius requires choosing a specific definition of the stellar surface, usually the Rossland radius, or the surface where the optical depth reaches a certain value. Additionally, the dust and gas around the star can contribute to the measured emission, potentially inflating the apparent size if not properly accounted for. And for very distant stars, even the Wilty may not have sufficient baseline to resolve the stellar disk, requiring astronomers to fall back on indirect methods. A third method, less commonly applicable but important in some cases, uses lunar occultations. When the Moon passes in front of, or occults, the star does not disappear instantaneously. If the star has a measurable angular size, its light diminishes over a very short but finite time interval as the Moon's limb crosses the stellar disk. By precisely timing the rate at which the star's brightness decreases during the occultation, astronomers can infer the star's angular diameter. This method works only for stars that happen to lie in the Moon's path across the sky, which is a fairly narrow band, so it is applicable only to a limited number of stars. But for those stars, it provides an independent check on other measurements. Antares and 119 Tauri are examples of supergiants whose sizes have been constrained using lunar occultations. A fourth method uses eclipsing binary systems. If two stars orbit each other, and their orbital plane is aligned with our line of sight, the stars will periodically eclipse each other, causing dips in the combined brightness. By analysing the shape and timing of these eclipse light curves, astronomers can determine the ratio of the stellar radii to the orbital separation. And if the orbital parameters are known, they can determine absolute stellar radii. This method provides some of the most precise stellar radius measurements available, but it requires the star to be in a suitable binary system, which many of the largest supergiants are not. VV Cephei and V766 Centauri are examples of eclipsing binary systems involving supergiant stars whose radii have been measured this way. Each of these methods has its strengths and weaknesses, its own sources of uncertainty and systematic error. When multiple methods agree on a similar radius for the same star, we can have high confidence in the result. When they disagree, it signals that something is not well understood, either about the star or about our measurement techniques. For the largest stars, the situation is often the latter, the uncertainties are large, the methods sometimes disagree, and the true radius remains a subject of active research and debate. This is not a failing of science, it is the frontier of science. It is the boundary between what we know and what we are still figuring out. And pushing that boundary outward, star by star, measurement by measurement, is one of the great ongoing adventures of human inquiry. Now I want to take you through the complete life story and death of a colossal star, because understanding how these titans meet their end is perhaps the most dramatic and consequential part of their entire existence. We have already discussed how massive stars are born in nebulae, how they burn through their hydrogen fuel on the main sequence, and how they expand into red supergiants as they begin to die. But the full story of what happens inside a massive star in its final years, months, days, and seconds is one of the most extraordinary narratives in all of physics. Let me tell it to you now. When a massive star, say one with an initial mass of 20 to 40 solar masses, leaves the main sequence and becomes a red supergiant, it does not simply stop fusing elements. On the contrary, the fusion process enters a phase of accelerating frenzy. Once the core hydrogen is exhausted, the core contracts and heats up until helium fusion ignites. Helium nuclei, also known as alpha particles, fuse together to form carbon and oxygen through a process called the triple alpha process. This helium burning phase lasts about 1 million years for a massive star. When the core helium is exhausted, the core contracts again, heating up further, and carbon fusion ignites. Carbon nuclei fuse to form neon, oxygen, and other elements. Carbon burning lasts about 1,000 years. After carbon, neon burning begins. Neon lasts about 1 year. Then oxygen burning, which lasts a few months. And finally silicon burning, where silicon nuclei fuse to form iron and other iron group elements. Silicon burning lasts approximately 1 day. 1 single day. After millions of years of hydrogen burning, millions of years of helium burning, thousands of years of carbon burning, and progressively shorter phases of neon, oxygen, and silicon burning, the star reaches the end of the line in a single day. At this point, the interior of the star looks like an onion, layer after concentric layer, each burning a different element. The outermost shell is still burning hydrogen. Below it, a shell burning helium. Below that, carbon, then neon, then oxygen, then silicon. And at the very center, like the pit of a cosmic peach, is a core of iron. Iron is special. It is the most tightly bound nucleus, meaning it has the lowest energy per nucleon of any element. When lighter elements fuse, they release energy because the product is more tightly bound than the reactants. But iron is already at the bottom of the nuclear energy curve. Fusing iron does not release energy. It absorbs energy. And splitting iron also absorbs energy. Iron is an energy sink, a nuclear dead end. When the core becomes predominantly iron, fusion can no longer generate the outward pressure needed to support the star against gravity. The tug of war that has defined the star's entire existence is about to end. And gravity is about to win. What happens next takes place in less than a second. Literally, the time from the onset of core collapse to the formation of a neutron star or black hole is measured in fractions of a second. The iron core, now about 1.4 solar masses, the Chandrasekhar mass, is supported by electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed too close together. But as the core grows and the temperature rises above about 10 billion Kelvin, two processes conspire to destroy this support. First, high-energy photons in the core begin to disintegrate iron nuclei in a process called photodisintegration. The photons are so energetic that they literally smash iron nuclei apart into helium nuclei and neutrons. This process absorbs an enormous amount of energy, robbing the core of thermal pressure. Second, The extreme density forces electrons to combine with protons in a process called electron capture, producing neutrons and neutrinos. This removes electrons from the gas, reducing the electron degeneracy pressure that is holding the core up. With both thermal pressure and electron degeneracy pressure suddenly reduced, the core has nothing left to resist gravity. It collapses. Catastrophically, the collapse is astonishingly fast. The inner part of the core, about 0.6 to 0.8 solar masses, collapses nearly homologously, meaning all parts fall inward at the same rate. Reaching speeds of about 70,000 kilometers per second, roughly a quarter of the speed of light. In about a quarter of a second, the inner core is compressed from a sphere roughly the size of Earth, about 12,000 kilometers in diameter, to a sphere only about 20 to 30 kilometers in diameter. The density reaches and exceeds nuclear density, about 230 million tons per cubic centimeter. A teaspoon of this material would weigh about 1 billion tons. At this point, the strong nuclear force between neutrons becomes repulsive at short distances, and the neutrons resist further compression. The collapse of the inner core halts abruptly. It bounces, like a ball hitting a floor. This bounce sends a powerful shockwave outward into the still infalling outer core. Meanwhile, the collapsed inner core has become a proto-neutron star, an incredibly hot, dense, neutrino-rich ball of neutrons about 20 kilometers across. The shockwave from the bounce propagates outward through the outer core, but it quickly loses energy. The infalling material from the outer core is raining down on the shock, decelerating it. And the shock is also losing energy to photodisintegration of the iron nuclei it passes through, the same process that contributed to the collapse in the first place. Within a few milliseconds, the shock stalls. It stops moving outward. It sits there, vibrating, a stalled shockwave about 100 to 200 kilometers from the center. And if nothing else happens, the shock will fade, the rest of the star will collapse onto the proto-neutron star, and the entire star will be swallowed into a black hole without any explosion. A failed supernova. This is thought to be the fate of some of the most massive stars, but for most massive stars in the relevant mass range, something saves the shock. That something is neutrinos. The proto-neutron star is radiating neutrinos at an absolutely staggering rate. In the first few seconds after core collapse, the proto-neutron star emits about 3 times 10 to the 53rd ergs of energy in neutrinos. To put this in perspective, that is about 10 times more energy than our Sun will produce in its entire 10 billion year lifetime. And all of that energy is emitted in just a few seconds. Most of these neutrinos stream out of the star without interacting with anything, because neutrinos are famously reluctant to interact with matter. But the density of the material just behind the shock is so extreme that a tiny fraction of the neutrinos, perhaps 5 to 10%, are absorbed by the gas. This absorbed energy heats the gas behind the shock, increasing the pressure and re-energizing the shockwave. Within about half a second to a second after the initial collapse, the revived shock begins to push outward again, and this time it does not stop. The shockwave, now powered by neutrino heating and the energy of the collapse itself, tears through the outer layers of the star. It accelerates the envelope, the hydrogen and helium-rich outer layers, to velocities of 10,000 to 30,000 kilometers per second. The star explodes. This is a Type II supernova, the violent death of a massive star with a hydrogen envelope. The explosion releases approximately 10 to the 51 ergs of kinetic energy, about 1% of the total neutrino energy, but still an almost inconceivable amount. The luminosity of the supernova peaks at about 1 billion solar luminosities, making it briefly as bright as an entire galaxy. For a few weeks, this single dying star outshines the combined light of the hundreds of billions of stars in its host galaxy. And then it fades as the expanding debris cloud, the supernova remnant, disperses into the interstellar medium. The explosion flings the star's outer layers into space at enormous velocities. This expanding shell of debris carries with it all the elements that the star forged during its lifetime: hydrogen and helium from the unburned envelope, carbon and oxygen from the helium-burning shell, neon and magnesium from the carbon-burning shell, silicon and sulfur from the oxygen and silicon-burning shells. And crucially, the supernova explosion itself synthesizes additional elements through explosive nucleosynthesis. The passage of the shockwave through the various layers triggers a brief but intense period of nuclear reactions, creating elements heavier than iron through rapid neutron capture, a process called the R process. Gold, platinum, silver, uranium, thorium, all of these elements are created in the few seconds of the supernova explosion and in the subsequent neutron-rich environment. They are flung into space along with the rest of the debris, where they will eventually be incorporated into new clouds of gas and dust, new nebulae, which will give birth to new generations of stars and planets. Every gold ring, every platinum necklace, every uranium atom in a nuclear reactor was forged in the death throes of a massive star. This is the ultimate cosmic recycling program. What remains at the center depends on the mass of the core. If the remnant mass is below about 3 solar masses, the result is a neutron star, one of the most exotic objects in the universe. A neutron star is essentially a giant atomic nucleus, about 20 kilometers in diameter, composed almost entirely of neutrons packed together at nuclear density. Its surface gravity is about 200 billion times stronger than Earth's surface gravity. A sugar cube of neutron star material would weigh about 1 billion tons. Some neutron stars rotate at incredible speeds, up to 716 rotations per second for the fastest known pulsar, and they emit beams of radiation from their magnetic poles. When these beams sweep past Earth, we detect regular pulses of radio waves, hence the name pulsar. The discovery of pulsars in 1967 by Jocelyn Bell Burnell was one of the most important discoveries in 20th century astrophysics. If the remnant mass exceeds about 3 solar masses, which is the Tolman-Oppenheimer-Volkoff limit, even neutron degeneracy pressure cannot halt the collapse. The core continues to shrink, passing through its own Schwarzschild radius, the event horizon, and forming a black hole. A black hole is a region of space-time where the gravitational field is so intense that nothing, not even light, can escape once it crosses the event horizon. The mass of the star is concentrated at a point of infinite density at the center, called the singularity, though most physicists believe that this singularity is a sign that our theory of gravity, general relativity, breaks down and needs to be replaced by a quantum theory of gravity at these extreme conditions. For the most massive stars, the ones with initial masses above about 25 to 40 solar masses, a black hole is the almost certain final fate. And for our colossal stars, the ones we have been discussing in this video, Canis Majoris, WOH G64, Stephenson 218, RSGC1-F01, all of them are expected to end as supernovae and leave behind either neutron stars or more likely black holes. There is a particularly spectacular variant of the supernova called a hypernova, which may occur when the most massive stars die. A hypernova is roughly 10 to 100 times more energetic than a normal supernova, and is often associated with a gamma-ray burst, a brief, intense flash of gamma-ray radiation that is the most energetic electromagnetic event in the universe after the Big Bang. Gamma-ray bursts can outshine an entire galaxy by a factor of 1,000,000 for a few seconds and can be detected from billions of light-years away. They are thought to be produced by relativistic jets, narrow beams of matter accelerated to near the speed of light, launched from the collapsing core of a massive star as it forms a black hole. Not all massive star deaths produce hypernovae or gamma-ray bursts. It likely requires specific conditions, such as very high mass, rapid rotation, and low metallicity. But the possibility that some of the largest stars could end their lives this way adds yet another layer of drama to their already spectacular biographies. Let me now connect this story of stellar death back to our personal existence, because this is where the narrative becomes truly profound. I mentioned earlier that the elements forged in massive stars are scattered into space when those stars die. But I want you to really deeply appreciate what this means. The carbon atoms in the organic molecules that make up your DNA were fused together from helium nuclei in the core of a star that exploded billions of years ago. The oxygen you are breathing right now was created in the carbon and neon-burning shells of massive stars. The calcium in your bones was produced during the explosive nucleosynthesis of a supernova. The iron in your hemoglobin, the molecule that carries oxygen in your blood, was the very last element fused in the core of a dying star before it collapsed and exploded. You are, quite literally, made of star stuff. This is not a metaphor. It is not a poetic exaggeration. It is a physical fact, established by decades of nuclear astrophysics and confirmed by measurements of isotope ratios in everything from meteorites to the sun's spectrum. Every atom in your body that is heavier than hydrogen, and some of the hydrogen too, was processed through at least one and probably several generations of stars before ending up in the gas cloud that collapsed to form our sun and solar system 4.6 billion years ago. The colossal stars we have been discussing, Canis Majoris and WOH G64 and their kin, are the factories that produce these elements. When they die, they will enrich the interstellar medium with a fresh supply of carbon, oxygen, silicon, iron, and all the other elements necessary for rocky planets, water, organic chemistry, and life. Some future star system, born from the ashes of these titans, may one day harbour a planet with liquid water and complex chemistry and, perhaps, conscious beings who look up at their own night sky and wonder about the stars. This is the grand cosmic cycle. Stars are born from the remnants of dead stars. Planets are formed from the same material. Life arises on those planets, built from atoms that were forged in nuclear fires billions of years ago. And one day, our own sun will exhaust its fuel, expand into a red giant, shed its outer layers, and return most of its material to the interstellar medium, where it will contribute to the next generation of stars and planets, and perhaps life. We are part of this cycle. We are not separate from the cosmos. We are made of it, literally, atom by atom, element by element. And the colossal stars, the ones we have been celebrating and studying in this video, are among the most important actors in this grand cosmic drama. They live briefly, burn fiercely, and die spectacularly. But in their death, they make everything else possible. Now, as we approach the final chapters of our journey, I want to take you beyond what exists today and into the realm of theory and speculation, because the stars we have discussed, as enormous as they are, may not represent the upper limit of what the universe has ever produced. There are theoretical objects, hypothetical stars that may have existed in the early universe that would dwarf even WOH G64 or Stephenson 218. And exploring these hypothetical giants will stretch our imaginations to their very limits. The first of these hypothetical objects is called a quasi-star, also known as a black hole star. This is a concept that exists only in theoretical models, but the physics behind it is fascinating and the implications are profound. A quasi-star is a hypothetical type of extremely massive star that may have existed only in the very first few 100 million years after the Big Bang. The idea is based on the following scenario. In the very early universe, the conditions for star formation were vastly different from what they are today. The gas was almost entirely hydrogen and helium, with virtually no heavier elements, because no previous generation of stars had yet lived and died to produce those elements. Without heavy elements, the gas could not cool efficiently. In today's universe, heavy elements in gas clouds radiate energy very effectively, allowing the gas to cool and condense into relatively small, modest mass stars. But in the early universe, without this cooling mechanism, gas clouds had to be much more massive before they could collapse. Theoretical models suggest that the first collapsing gas clouds could have been millions of solar masses or more, potentially giving rise to individual stars or protostellar objects of unprecedented mass. Now here is where it gets interesting. Imagine a protostar that is accreting material at an extraordinarily high rate, much higher than anything we see in star formation today. As the protostar grows in mass, its core becomes hotter and denser. At some point, the core might become so massive and so hot that it collapses directly into a black hole. In today's universe, when a core collapses into a black hole, the rest of the star usually follows, either collapsing entirely or being blown apart in a supernova. But in the unique conditions of the early universe, with extremely rapid accretion of pristine gas, something different might happen. The material around the newly formed black hole might continue to feed it at a prodigious rate. As material falls into the black hole, it forms an accretion disk, and the gravitational energy released by this accretion is converted into radiation with extraordinary efficiency. This radiation, this energy from the accretion process, takes the place of nuclear fusion as the energy source that supports the star against gravity. The outer envelope of the quasi-star is supported not by fusion, but by the energy released from matter falling into the central black hole. And because accretion can release more energy per unit mass than fusion, the quasi-star can be far more luminous and far larger than any normal star. Theoretical models of quasi-stars predict that they could have had radii of 7,000 to 10,000 or more solar radii. Some more extreme models push this to 30,000 or even higher. Let me put that in perspective. 10,000 solar radii corresponds to a radius of approximately 46 astronomical units. For context, Pluto orbits the Sun at an average distance of about 39.5 AU. Neptune is at 30 AU. Uranus is at about 19 AU. So a quasi-star at 10,000 solar radii would have a photosphere that extends well beyond the orbit of Pluto, engulfing the entire solar system. The diameter of such a quasi-star would be approximately 92 astronomical units, or about 13.8 billion kilometers. Light would take about 12.8 hours to travel from one side to the other. This is a star larger than our entire planetary system. At 30,000 solar radii, the quasi-star would extend about 140 AU from its center, reaching into the inner regions of the Kuiper belt. At this scale, the distinction between a star and a small nebula starts to blur. The object would be more like a vast, luminous gas cloud with a black hole at its heart. A cosmic engine of unimaginable power and scale. The effective temperature of a quasi-star would be relatively moderate, perhaps 4,000 to 6,000 Kelvin, because the enormous surface area distributes the energy output over such a vast surface. Despite being unimaginably luminous, the temperature at the surface would be similar to or only slightly hotter than our Sun. The light from a quasi-star would appear white or slightly yellow-white, not red like the supergiants we have been discussing. It would be a strange and beautiful object, a gentle, warm glow surrounding a central darkness. The ultimate irony of a star powered not by creation, by fusion, but by destruction. By the devouring gravity of a black hole. Quasi-stars would not have been long-lived. The central black hole would grow rapidly, consuming the surrounding material. As the black hole grew, the energy output would change, the envelope would evolve, and eventually, perhaps after a few million years, the entire quasi-star would be consumed or disrupted, leaving behind a massive black hole, perhaps thousands to tens of thousands of solar masses. And this is the key to why quasi-stars are not just a theoretical curiosity. They may solve one of the biggest puzzles in modern astronomy, the origin of supermassive black holes. Supermassive black holes are the monstrous gravitational engines that lurk at the centers of galaxies. The supermassive black hole at the center of our own Milky Way Sagittarius A star has a mass of about 4 million solar masses. Other galaxies harbor even more massive beasts, some with masses of billions of solar masses. These objects are huge. And the puzzle is that we observe them existing at very early times in the universe's history, when the universe was less than 1 billion years old. If you start with a stellar mass black hole, say 10 to 100 solar masses, and try to grow it to millions or billions of solar masses through normal accretion, There is a fundamental limit called the Eddington limit that restricts how fast a black hole can eat. Even accreting at the maximum Eddington rate, it takes much longer than 1 billion years to grow from 100 solar masses to 1 billion solar masses. So how did these supermassive black holes form so quickly? One possibility is that they grew from massive seeds, not from the tiny black holes left behind by normal stellar deaths, but from much more massive objects. Quasi-stars, if they existed, could have provided exactly these seeds. A quasi-star that starts with a small black hole at its center and feeds it for a few million years could produce a black hole of thousands or tens of thousands of solar masses. These intermediate mass black holes could then continue to grow through accretion and mergers, eventually reaching the supermassive regime. Quasi-stars might be the missing link in the black hole growth story, the cosmic incubators that hatched the universe's most massive gravitational giants. There is no direct observational evidence that quasi-stars ever existed. They are purely theoretical at this point. But the physics is sound, the models are self-consistent, and they elegantly explain a real observational puzzle. And if they did exist, they were almost certainly the largest stellar objects the universe has ever produced, dwarfing even the most colossal red supergiants of today by factors of 5 to 20 or more. The James Webb Space Telescope, with its unprecedented infrared sensitivity and its ability to peer into the very early universe, might eventually find indirect evidence for quasi-stars or their remnants. It is one of the great open questions in modern astrophysics, and the answer could reshape our understanding of how the universe's largest structures were built.